Hi everyone, I'm Minjian Wu, a senior engineer from Penspen. At Penspen, we provide a range of consultancy services to the oil and gas sector. And one of the services that we provide is QRA, Quantitative Risk Assessment. As of myself, I've been doing QRAs for the past few years, and today I'm presenting to you Quantitative Risk Assessment for high pressure gas pipelines in Europe. Next slide, please, Annie. So here we are seeing a map for the gas pipeline networks across Europe. The map shows the gas transmission network in dark blue, overlaid with the gas distribution network in light brown. The thickness of the colored lines denotes the pipeline diameter, and the background colors indicate EU member states. And of course, UK will soon be grayed out. We can see that there are quite a number of significant pipelines supplying large amount of gas to the continent. The point to note here is that this map was from data in 2009. I have to say that the first time when I saw this image, I was surprised by the volume of gas pipelines running next to us 10 years ago. Next slide, please. Why is gas important to us? The world is going through a period when research in energy is overarching. Oil and gas prices are volatile because of geopolitical and financial crisis. The rate of worldwide energy consumption has been accelerating, while gas resources are dropping fast. Concerns about national supply and security of energy are on top of the political agenda, and global climate changes are now believed to be caused by the release of greenhouse gases into the atmosphere. Yet, natural gas is often the energy of choice of home heating, and it's increasingly being used instead of oil for transportation. Although renewable energy sources offer the best cuts in overall carbon dioxide emissions, the generation of electricity from natural gas, some other types of greenhouse gas such as hydrogen instead of coal, can significantly reduce the release of carbon dioxide to the atmosphere. As the demand for natural gas rises in Europe and the rest of the world, it becomes more important to gain insights into the transportation of gas and the risks associated with it. Historically, critical infrastructure networks have evolved under the pressure to minimize local rather than global failures. However, little is known on how this local optimization impacts network robustness and security of supply on a global scale. The failure of a few important links may cause major disruption to supply in the network, not because these links connect to the grid hubs, but because they're part of major transportation routes that are critical to the operation of the whole network. Next slide, please. Now, how safe are gas pipelines? Let's look at some statistics. Data from the National Transportation Safety Board indicate that only a small percentage of fatalities related to transportation came from pipelines. Within that, about half came from gas pipelines. So relatively speaking, transportation by gas pipelines are safe. Next slide, please. But relatively safe doesn't mean nothing bad can happen. Data published by PHMSA, the Pipeline Hazardous Materials Safety Administration, indicate that a constant number of people are injured and killed from pipeline incidents every year, and some incidents have costed the operators over $1 billion. The costs include damage to the pipeline system, emergency response, cost of lost product, and damage to property not owned by the pipeline operator. Generally, the pipeline operator also reimburses the public for all public costs. In summary, a pipeline failure will potentially not only result in lost product, but cause life losses and impose an enormous amount of costs. Next slide, please. So here are some examples of pipeline failure escalating to catastrophic events. On the top left, we can see fire engulfing houses with firefighters scratching their heads, thinking, how are we going to put out this fire? The fire was likely to be triggered by an ignition source in a house following a burst mains. An explosion was also likely down the line because gas was likely released to an enclosed space. In the other pictures, we can see the horrific aftermath from pipeline failures. It's worth pointing out that none of these would have happened if there was not an ignition source present. However, in the real world, this is rarely the case. Next slide, please. Now let's go over some reported pipeline failure accidents. This one is from New Mexico in August 2020. There was a failure in gas pipeline due to microbial internal corrosion and caused 12 fatalities. The operator was fined over $15 million, followed by another $86 million on system modifications. Next slide, please. And here's another accident in Belgium in July 2004. This was a failure in gas pipeline due to mechanical damage and caused 24 fatalities. Next slide, please. Here's a more recent example. In fact, this one happened just half a year ago in the States. A 13-inch diameter natural gas transmission pipeline ruptured at Girthweld. The resulting fire burned vegetation over 5 acres of heavily forested land. Luckily, probably due to its remote location, there were no injuries, fatalities, or evacuations. About 148 million cubic feet of natural gas was released during the rupture and the resulting emergency blowdown. What's interesting is that a parallel pipeline in the same right-of-way ruptured at a location just some tens of miles away in August 2019, so it was just a year apart. In that 2019 accident, 1 person was killed and 5 nearby residents were injured when the rupture released natural gas and ignited. Investigations into whether these 2 events are related are still ongoing. Although nobody was killed or injured in the most recent 2020 accident, costs associated with the pipeline being forced out of service will be significant for the operator. Next slide, please. Now let's pull those horrific scenes back on the screen. So nobody wants to see a pipeline fail, but with all kinds of evolved managerial and physical controls in place in attempt to stop a failure and prevent escalation from failure, pipelines still fail. Sometimes it's just a random thing. One must then wonder, what if we just do every single safety control possible on this planet? Well, whoever's paying for doing them surely don't want the cost to go over the roof. And really, what chance is there that nothing will ever happen? The fact is that failure cannot be eliminated. We can only drop the prospect of a pipeline failure to its minimum by doing so much that we can do. Next slide, please. So now we've arrived at this rather philosophical question of the modern world. How much is enough? How many safety controls do we need to put in place to drop the occurrence of failure to its minimum? And how do we know that it's at its minimum level? What quantifies the minimum level? Well, in fact, all along, we've been talking about chance of failure and causing harm. It's time that we brought up the concept of risk. Next slide, please. By definition of the Oxford Dictionary, risk is the chance of loss. So there is an element of chance and element of loss. In engineering terms, risk is a function of the probability that a hazard will occur and the consequences of the hazard, whereby a hazard is something with the potential to cause harm. Simply put, risk is a product of probability and consequence. It is a key numerical indicator of effectiveness of any safety controls implemented on the pipeline. So earlier on, when I was raising the question of how much is enough, the how much is quantified by the risk value. And the process of calculating that how much is called QIA, Quantitative Risk Assessment. This differs from the more commonly seen qualitative risk assessment, where risks are usually indexed with a matrix. The QIA is largely mathematical with the application of statistics, physics, and chemistry. This may sound a bit complex, but really, down to the end, it's just playing with numbers, which I'm sure many of you are doing on a daily basis. Next slide, please. So why do we assess risk? Not just assess the chance of failure or chance of causing fatalities on their own, but assess the combined product. And why do we care about its numerical form? I've largely gone over the reasoning behind this in the previous slides, but there are a few other factors that we need to consider here. In summary, primarily, we need to think about the triad of society, the economy, and the environment We need to reduce or prevent casualties, reduce costs where possible to maximize profitability and protect the environment. And then there's a need to improve effectiveness of an integrity or safety management program for an asset. Next slide, please. And then there's also the requirement for compliance with legislation and standards. The UKHC traced back a long time, probably one of the longest in Europe, for developing safety regulations, and there are a few examples for gas pipelines, the PSR, the PSSR, and the COMA regulation. The British Standard PD 8010 Part 4 guide to the application of pipeline risk assessment to proposed developments in the vicinity of major accident hazard pipelines containing flammables is also a key reference. The Institute for Gas Engineers and Managers, the IGEM, have also published a number of codes and standards for pipeline design, construction, commissioning, and risk assessments. Sometimes you can find overlapping material between these codes, and it's reasonable, given that they are the industry's best practice. Pipeline owners and operators are usually required by regulators to do a risk assessment when a pipeline runs next to a populated area or is in close proximity to a residence, or when there's deviation from design, and the deviation must be justified with a risk assessment. Next slide, please. Now, before I jump into how to do a QRA, let's revisit the definition of risk. Risk is, in the context of QRA, the product of failure probability and consequence. So how do we calculate this risk? British Gas had initiated to look at establishing a QRA methodology back in the 1980s. And that methodology has been further developed since then. The current methodology that us in Penspen adopt can be simplified to the flowchart on the next slide. Next slide, please. If you look at it closely, it is just an expansion of that tree diagram from the previous slide. The flow of steps goes from the left to right and back to the left in a closed loop. The starting point is identification of hazards. Can it be a corrosion? Is it external? Is it internal? Could it be mechanical damage? Could it be a third-party damage? From the previous failure examples, for example, that one in New Mexico, the failure was due to internal microbial corrosion, and the one in the States was due to failure at a girth weld. After identification of hazards, we identify the failure mode. Is it a pinhole leak, a small hole, a large hole, or the full diameter rupture? For each hazard and failure mode, we can derive the failure frequency. The failure frequency is also dependent on the pipeline properties and the existing controls, such as slabbing, for example. For each hazards and failure modes that we identify, there are different outflow behaviors as well. For dispersed gas from an outflow, the gas can either be ignited or not. If the gas is not ignited, the gas will simply be dispersed into the air and nothing happens. If the gas is ignited, there's a chance that there's an immediate ignition and also a chance that there's a delay. For immediate ignition, there will usually be a fireball followed by a jet fire. For delayed ignition, there will just be a jet fire. The fires will have thermal radiation impacts on people, and that can kill. The number of fatalities combined with pipeline failure frequencies can get us a risk profile for an individual and for the wider society. The risk profile can be compared against certain risk acceptance criteria to see if the risk is acceptable or intolerable or somewhere vaguely in between. In case that the risks are above the acceptance criteria, we need to think about risk mitigation measures to reduce risks. For example, slabbing, relaying heavier wall, or increased surveillance frequency. Of course, each of these measures will have cost implications, and for that, we'll need to do a CVA to find out if the costs are proportional to the reduction in risk. And then to calculate the reduction in risk, we need to go back to the start of the loop and calculate a new risk profile based on the mitigation measure being implemented. Now, before I go into more details on each of the steps in this flowchart, let me first introduce the software that Penspen used to do ORA studies. Next slide, please. We call it Penspen Integrity PI Risk, and is currently version 2. The tool calculates the individual and society risks for actual locations of pipeline and population, and allows mitigation options to be explored. Its consequence models are fully validated against HC MISAP 12, which is the model for the estimation of individual and societal risk from hazards of pipelines. It's got a graphical interface where pipeline route and design parameters can be added to a georeferenced drawing or aerial image, and the population and shelter around the pipeline can be directly added via Google Earth. The tool internally calculates failure frequencies, transient outflow, and associated thermal radiation, and hazard distances by integrating thermal flux over time and distance. I'll explain these terms in later slides. The output can be exported to Excel for post-processing. As we're engineers, we always need to apply our engineering judgment. The tool is just there to help us do the work. Next slide, please. So let's go back to the methodology. There are various methods to identify hazards and threats. For example, the FMEA, the fault tree analysis, what hazard. The typical gas pipeline hazards in Europe are external corrosion, mechanical defects from manufacturing, construction, material, and also ground movement from landslides, earthquake, and then there's the most difficult and most unpredictable mechanism, the third-party interference. Organizations such as EUCOPA in the UK and EGIG in Europe provide database for third-party interference damage. Next slide, please. There are various methods for predicting the pipeline failure frequencies, and this one is based on the HSE Research Report 1036 called PIPIN, Pipeline Integrity, which is a computer code essentially. Next slide, please. There's also the statistical analysis approach based on data from EUCOPA. This is particularly useful to assess pipeline failure frequency from third-party interference. The logic behind is that pipeline damage due to external interference can occur in the form of gouges, dents, or dent-gouge combinations. Third-party damage is random in nature, and the predictive model is often used to calculate leak and rupture failure frequencies for specific pipelines. The predictive models would use gouge and dent-gouge fracture mechanics models to predict the pipeline probability of failure, which is also dependent upon the pipeline geometry, material, properties, and operating pressure. The EUCOPA database includes reports of external interference incidents, including the type of damage, the size of the damage, and the number and location of the incidents. The database was then analyzed to determine the best fit distribution and corresponding distribution parameters for the plane gouge length and depth, gouging dent gouge length and depth, and dent force models. These probability distributions allow third-party interference failure frequencies to be derived. Apart from these, an estimate of the third-party hit rate, which is also dependent on location class, so either rural or suburban, and depth of cover, also plays a part in the statistical model for predicting third-party interference failure frequencies. This is part of the reason why site-specific motivation factors need to be considered. Next slide, please. So here are some example motivation factors from IGMTD2. The plot on the left shows reduced failure frequency reduction factor with increased pipeline depth cover, the benchmark is at 1.1 meters of burial depth. And the plot on the right shows reduced reduction factor with increased surveillance frequency. The benchmark is at a 14-day surveillance interval. So, in other words, once per fortnight frequency. Next slide, please. From a pipeline failure, depending on the mode of failure and chance of ignition, there are different outcomes. The diagram provides a simple event tree for a natural gas pipeline. And as you can see, for ruptured pipeline, if gas is ignited immediately after the release, it'll create a fireball, followed by a jet fire when the fireball dies out. And if the gas is not immediately ignited, then only a jet fire will be created. For a whole leak, released gas followed by ignition will just create a jet fire. If the released gas, either from a ruptured pipeline or from a whole leak, is not ignited, then the gas will simply be dispersed into the air. Next slide, please. The HEC Research Report 1034 gives a more detailed breakdown of events following pipeline failure. And they also assign a range of ignition probabilities to the gas ignition events. There are some other models that can calculate ignition probabilities based on pipeline operating pressure and diameter. For example, this PD squared equation model on the left. But such equations can sometimes give underconservative values. By underconservative, I mean a slightly greater chance that the gas is not ignited. Next slide, please. A pipeline failure giving rise to gas release, if followed by ignition, can escalate to serious consequences. The consequences are modeled using Penspen's in-house software PI risk, which is built upon HEC's consequence model MISHAP 12. The consequence modeler starts with simulation of the transient outflow of gas from a leak or rupture. The plot on the top right shows an example gas outflow with time from a ruptured pipeline. As you can see, the initial mass flow rate is very high, which can facilitate build-up of a fireball. This flow rate then drops exponentially with time and gradually plateaus, by which time the fireball has gone away and a steady state jet fire begins to take form. Both the fireball and the jet fire radiate heat to a certain extent, and the latter tends to have longer lasting effects on its surroundings, including buildings and human beings, either indoors or outdoors. The HEC finds a thermal radiation flux of 25.6 kilowatts per meter squared for spontaneous ignition and 14.7 kilowatts per meter squared for piloted ignition of wood. The spontaneous ignition means that a building will be burned down, and then people inside of it will become a fatality. Whereas the piloted ignition means that a building will catch fire, but any people inside will have a chance to escape. However, once they're outside, they'll be subject to thermal radiation. For people that are not in the building, the fatality criteria are defined by the thermal load a person receives. The thermal load is described by a parameter called thermodose unit, which is essentially integration of radiation flux over time and distance for an escaping person. For a vulnerable person, for example, the elderly, children, and the ill, they have a lower tolerance to thermal radiation. There are, of course, other potential consequences, for example, release of pressure energy and flying missiles generated from overlying soil or from pipe fragments, but these are generally found to be negligible compared to fire. On the bottom right, I'm showing you a screenshot from Penspen's PI risk, and it shows you some example results from consequence modeler. Next slide, please. So this is an example software output shown on Google Earth. The effect contours for buildings and people are plotted in color for visualization. The dark line in the middle is the gas pipeline, and the red lines are the spontaneous ignition distances from the pipeline, and the green lines are the piloted ignition distances from the pipeline. So any building that's between the red lines will be burned down, and any people inside of it will become fatalities. However, any building that's between the red lines and the green lines will catch fire, but won't be burnt down. So the people inside will have a chance to escape, but be subject to jet fire once they're outside. The green lines and the pink lines are the standard population escape distance and the vulnerable population escape distance. So any people that's outside of the pink line, including the vulnerable people, they will be regarded as safe. For that building on this map, because it's outside of the green lines, it will not catch fire, and any people inside will not become fatalities. So the building will provide shelter for people in this case. The point to note here is that for this building, the section of the pipeline with hazard distances impinging on the building must be included for risk assessment. The length of that pipeline section is called the interaction length. Next slide, please. So now that we have the failure and ignition probabilities calculated, and we've also calculated the thermal radiation hazard ranges, knowing that anyone within the relative hazard ranges will become fatalities, we can calculate risk. There's the risk to the individual, which is measured with a risk transect normal to the pipeline, and there is the risk to the wider society, which is measured with an FN curve or a risk integral of F and N. This FN curve represents the frequency of N or more fatalities. Note that the emphasis is on N or more fatalities versus the number of fatalities, N. Next slide, please. So here is a simple representation of how an FN curve is generated. Let's suppose that the chance of having more than 10 fatalities is 0, but the chance of having, give or take, 10 fatalities is at 0.01. The chance of having 10 or more fatalities would then be 0.01 plus 0, which is 0.01. And the cumulative frequency, the capital F, and marker 10 on the n-axis would be 0.01. Then let's say that the chances of having 9, 8, 7, and 6 fatalities are all 0. The cumulative frequency F would stay at 0.01 for these n-axis markers. Then let's say that there's a chance of having 5 fatalities and it's at 0.02. The cumulative F at n-axis marker 5 would be 0.02 plus 0.01 plus a number of zeros in between, which then result in 0.03 at marker 5. Then say that the chances of having 4, 3, and 2 fatalities is 0, but having 1 fatality is 0.04. The cumulative F at 1 fatality would at last be 0.04 plus 0.02 plus 0.01 plus a number of zeros, which then is 0.07. Note that the area under the curve is a risk integral, sometimes being referred to as the expectation value or the potential loss of life, and it's an important indicator of risk when we come to the cost-benefit analysis later on. Next slide, please. So now that we've calculated the individual and societal risk, we need to determine if these are acceptable by comparing the risk profile against certain acceptance criteria. The criteria are usually set out by regulations, code guidance, or other industry practice. The HSE says that if the risk is above 10 to the power of -3 for worker or 10 to the power of -4 for public, then the risk is regarded as intolerable. However, if the risk is below 10 to the power of -6, the risk would be broadly acceptable. And if the risk is anywhere between, it will be tolerable only if allowed. So the key here is that only if allowed. We need to demonstrate allowed, which is the as low as reasonably practicable, in order to demonstrate that the risk is tolerable. The IGMTD1 gives the societal risk criterion, whereby if the FN curve, the societal risk FN curve, is under this red line, it would be broadly acceptable. But if it's above or cross over the red line, it will be acceptable only if allowed. Next slide, please. Here is an example individual risk transacts plot and an example societal risk FN curve. On the left, we can see that the individual risk transacts is well below HEC's broadly acceptable criteria of 10 to the power of -6. However, on the right, we see that the FN curve crosses over the boundary line and it falls upon the acceptable if allowed region. So for that reason, we'll need to demonstrate allowed and then to demonstrate acceptance or tolerability. Next slide, please. So for the allowed analysis, which is demonstration of the allowed and then the tolerability, first we'll need to come up with a range of options to mitigate risks. Typical ones include relay pipeline with heavy wall, install slabbing, relay increased depth of cover, or reduce surveys. Remember that the risk is a product of failure probability and consequence. So by reducing either or both of them, you can reduce risk. Each of the mitigation measures would of course have its own cost implications, and hence we need to do CVA's cost-benefit analysis to justify if the measures are also cost-effective. And from that, we can determine if the attribute risks are allowed. Next slide, please. Cost-benefit analysis is essentially finding out the ratio between cost and reduction of risk. This ratio is normalized to a non-dimensional number, usually goes by a term called the disproportion factor. Regulatory guidelines usually set a threshold value for this factor, whereby if the calculated factor is greater than the threshold value, it would deem the measure non-economical and not worthwhile. The existing risk will then be considered allowed and hence tolerable or acceptable. The table at the bottom of this slide is an example CVA calculation for slabbing mitigation measure. The original potential loss of life, or the expectation value, remember from the previous slide, is the area under the societal risk FN curve, and this value is calculated to be this much based on the attribute pipeline settings. The reduced PIL, the potential loss of life, is calculated to be this much based on the pipeline being slab protected. The difference in risk values between the two is this much, and installation of slabs would cost this much. The resulting disproportion factor is then this much. This is in the order of hundreds, so it's too high for slabbing to be reasonably justified. If other mitigation measures yield similar results, we would then say that the risks on site are considered allowed and tolerable. No further actions or capital expenditure would be required in this case. Next slide, please. Now let's wrap up. So first, we identify hazards, and then we calculate failure frequencies and calculate consequences in terms of fatalities. And then we compute risk and compare that risk against some risk acceptance criteria. then we will try to mitigate risk. By doing that, we need to do CBAs to see if any risk mitigation measures can be justified. And the end result is a business case if something needs to be done to improve pipeline safety and pass regulator approval. Thanks, everyone. Any questions, please?